Okay. All right. Um, Also, I just wanted to tell you, I just posted something onto the class folder. You just take a look. It's about the final test, which will be a pen and paper test. More details can be found in my post, right? Okay. Um, uh, Also, I wanted to tell you another thing, right? I mean, you know that the first test was conducted out of 18, and then it was converted back to 15, and there was some at least one issue in one of the question papers, which I promised that I will take care of. I have done it. Okay. And then let's assume that there is some faculty. Okay. And then there are students. Now, there are two things. Once the faculty says that he or she has taken care of it, and the students believe him or her, or the other way around, the students still cannot, believe that person, but they start talking about the particular test, airing their confusion in a WhatsApp group. So what can snowball out of such WhatsApp conversation, which that faculty is not part of? And by the way, I do not want to be part of any student WhatsApp groups. Okay. So what will happen is, I mean, you haven't really asked for clarification from the faculty, right? And then you are trying to, because you are anxious, you are trying to form your own opinions, which is, I mean, doesn't really have a basis. I'm okay with that, right? But I mean, as I said, the grades have been adjusted accordingly. Okay, I mean, addressing all of your concerns. Now, if you still don't believe me, you got to send an email to the TA. In this particular case, Pavan, because Farha was busy during the first test, she had her own exams to write. So Pavan knows the grades, right? So if anyone has a doubt about his or her grade from the first test, right? He or she should send an email to Pavan Enuganti, and Pavan will let that person know about the grade. Okay. I, as a person, am not comfortable uploading the entire CSV file to the class group or to some common email ID, because I am, trained to respect people's privacy. You understand my point? Okay. So I will never upload the entire CSV file, which not only shows your grades, but it also shows the grades of your friends. I will not do it. Okay. And that is precisely the reason I understand that this is a common practice in most places in India, but I'm not comfortable with this practice. Okay. So I hope I have made myself clear why I haven't uploaded the grade sheets. But if you have any question about your particular grade from test 1 or test 2, you can send an email to Pavan, and Pavan will let you know your grade. Okay. All right. Homework 2 is yet to be graded. I will do that. Okay. I'll grade homework 2 and homework 3 together, and then I'll post the grades of the homework. Okay. All right. All right. Okay. So I hope this sort of assuages your concerns. Okay. All right. Yeah. Okay. Yeah. The 5-minute point is, let's say the exam is for 2 hours. Okay. So you can upload, if you finish before that, you can upload your test and immediately leave the classroom. If you take the full 2 hours in finishing the exam, then I can only give you 5 minutes to upload the PDF, okay, and email it to the TA. I cannot give you more. I'm really sorry, because I'm concerned about a lot of other things. Okay. Now, the quickest way to do that, because I know there could be, some issues in internet and blah, blah, blah. The quickest way to do that is that as soon as you finish one question, right, immediately use your mobile phone camera to scan it and save it as a PDF. I mean, you are using these softwares like Advanced Lens and whatever, right? Okay. And then you start the next question, finish the solution, and scan it. And you can keep adding those documents to your, scanning software, right? And then as soon as you finish, you're actually, let's say there are 5 questions. So you have 5 different PDFs and you can merge, right? I mean, you don't really have to merge, the software itself takes care of it. And then your PDF is ready. Okay. and then you email it straight away to the TS. In this case, Pavan and Farha, they will download those solutions and upload to a drive which is only accessible to me. Okay, all right. Is that clear? I cannot give you more than 5 minutes after the test is done. And once again, I mean, if you are prepared enough, you should be able to finish the test well before the stipulated time. So you'll have enough time to upload the, so your solutions anyway. Okay. All right. Okay. Okay. So enough of class talk. So let's just start talking about some of the things. So we will continue with our examples, and I'll leave you early, as I said. So okay. So let's say V is a vector space with an inner product. Okay. V is a vector space with an inner product. Okay. And I have a linear transformation that is between V and V, right? And this is orthogonal. All right, which means that this guy T preserves length. Okay, which means that any orthogonal transformation, if you recall, satisfies this property. We have seen this earlier, right? Okay, so for any vector V that belongs to the vector space V. All right. So what I want to see is that this guy T preserves the inner product itself. That is, I mean, if I choose two vectors W and V, for two vectors W and V in V, right? The inner product of TV TW is nothing but the inner product of inner product of TW right? TW TV is nothing but the inner product of W and V. Okay, all right. And then I also want to show that T preserves distance. Okay, I also want to show that such an orthogonal linear transformation preserves distance. Which means that if I take any two output, TV and TW, right, that is nothing but the distance between those TV and TW is nothing but the distance between V and W. Okay, all right. Now, since T since T is orthogonal, right, we know that the norm of TV is nothing but is equal to norm of V. What this implies is that the inner product of TV with itself, right, because that is how you define the norm, is the inner product of V with it. Now, just take V as W plus, just replace V with W plus V. So you just think of a vector which can, because this V is a placeholder, it's just arbitrary, right? Okay, so you just replace this V right V as W plus V. It's just a dummy variable. Think of V as a dummy variable. So what you will get is the following. By just using the inner product property of orthogonality, right? Okay. And then what you have is, you know, T of W plus V, because it's a linear transformation, it's nothing but TW plus TV, and the same, right? Okay. So you have, this is TW plus TV, and this is also TW plus TV. So you take the inner product, and you know by the properties of the inner product, you have a bunch of these inner products, right? Correct. And then here also you will get the same thing. Okay. Now what we know is that because T is orthogonal, right? The norm of TV is equal to norm of V, which means the inner product of TV with itself is the inner product of V with itself. So the inner product of TW with itself will be equal to the inner product of W with itself by the same property. And sorry, this will be V. This will be V. And the inner product of T, in fact, what did I do? So this is EV. So this will be equal to, right? So these things go away, 2 will cancel out, and what you are going to have is the inner product of, really sorry about this. The inner product of okay, and thus you show that T preserves the inner product. That is number 1. Number 2 is T preserves the distance. Now the distance between these two guys, EV and TW, is nothing but PV minus TW, right? In the norm, right? That is how you define the distance, okay? In the Euclidean norm. Now what will happen is, this is because T is a linear transformation, you can rewrite it this way, and then by using the same property of orthogonality, this is nothing but V minus W, right? Okay, and by definition, this guy is nothing but the distance between V and W in the L2 norm. Okay, and so therefore T preserves distance as well. Okay. Okay. Yeah. Okay. An example 2 is that we now have a V over a set of reals. So V is just a real vector space, right? And there is an inner product that is defined on such a vector space, right? So V is equal to R. Okay. Now, I define the transformation in the following manner, the linear transformation, right? And I say that this denotes an isometry. This denotes, and this is nothing but an isometry. Okay, all right. Now, what is an isometry? An isometry is nothing but for two vectors u and v, right? If the inner product is preserved, which is what we have seen earlier, right? For u and v in V, then this is called an isometry. Okay, all right. So this we know. Okay. Now, I mean, I have a claim. This is what I'm claiming, that all eigenvalues of T, right? All eigenvalues of T will satisfy this equation. Okay. So we'll just start with the definition of the isometry, right? Which is, I mean, I know that this is my linear transformation. I also know that the inner product of TUTV is equal to the inner product of U and V, right? And we know that the eigenvalue eigenvector equation, which is TU equal to lambda U, TV equal to lambda V, right? And now I start using the property of the inner product. So remember, this is a real vector space, right? So I pull out the first scalar, right? And then this guy, if I pull it out, it is just lambda bar, correct? By the property of the inner product. Now this implies I have lambda bar minus 1. Now this guy is actually a non-trivial inner product, right? I really don't care if this guy is 0. So I would by default assume that this inner product is not 0, right? Unless otherwise specified. So that means that lambda bar minus 1 equal to 0, and that means that modulus of lambda squared equal to 1, and that means that the absolute value of lambda satisfies this equation. Okay, all right. Okay. Now, the same property, let's assume that I have a same property, right? Under the same assumptions of isometry, can you also show that T is non-singular? So under the same assumptions of isometry, under the same assumptions on isometry, can you show that T is T non-singular? Okay. Okay. Now, please do not confuse yourself with the first example. I really do not know if T is orthogonal or not. So I just know that I have been given a linear transformation, okay, on a vector space, right? An inner product is defined, and I am told that the transformation satisfies isometry, which means that I know what I know is EUTV is equal to U. This I know. This much I know. Okay. All right. And so how do I show that this is non-singular? What would be the approach? You don't have to tell me the exact proof, but if you can tell me the approach, I would be happy. What would be the approach? Since it's an isometry, I know this, right? I know this, right? This is an isometry. So I know this, correct? So I'll just use the same trick, which is it's just a placeholder, right? Um, actually, I think uh, I can rewrite this, right? It's an isometry, I know. So it's TV, TV, VV. So if I just choose the same vector, right? I mean, I can just assume that this is true, right? Okay. And then what I'll do is I'll just, instead of V, I'll just say V equal to U plus V. Okay. So what I will have is that the same thing, the same trick, right? Okay. And then if I expand this out, what I will have is TU plus TU oh no. So TU right, plus TU plus TV equal to UU plus UV plus VU plus V. Right? I mean, it's just a simple expansion. Now, I mean, what do I know? I know this, right? This is given to me, that the inner product of TV is equal to the inner product of VY. So by using this, I can also argue that the inner product of TU is equal to the inner product of U and U, right? So using that simple property, what I see is that there are terms on the left and right that will get cancelled out, right? And then from here, I can easily argue that I have TU is equal to U. Okay. Now, so that this implies that T is orthogonal, if you recall, right? If you recall that T is orthogonal. And so more importantly, what I can just say is that norm of TV, because since T is orthogonal, norm of TV is equal to the norm of V, right? Okay. Now, if TV equal to 0, let's say, if TV equal to 0, then that implies that norm of V equal to 0. And this will imply that V has to be equal to 0 identically. So that means if TV equal to 0, I get V is equal to 0, which means what? Which means that T is a one-to-one map. If T is one-to-one map, then that means T is invertible, which we know already, right? And that means T is non-singular. Okay. All right. Okay. Now, what I wanted to do is pick up something. Where did that example go? Oh, oh.
So,
Yeah, yeah.
so why did we prove TUT, a dot product of TUT is equal to U comma V, dot product of U comma, that's given in the question, right? Because of isometry.
No, what was given in the question was actually slightly, what was given in the question was dot, I mean, the inner product of TV and TV is equal to inner product of V and V. That was given.
Okay, so the question is different, right? We can't
Right,
use the same assumptions of
right,
isometry.
right, right, right. Okay, I just, where did I leave that example? Oh, damn it. Ah, okay. All right. So okay. Yeah. So let's look at this. Let T, this is example 3. Let T is a linear transformation, right? T is linear and it also satisfies T square equal to I. I mean, such transformations are known as idempotent transformation, but you really don't, I mean, if you don't know the terminology, I mean, it's okay, all right? So I have two propositions. Proposition 1 is that if T minus I is a non-singular map, then T of V equal to minus V is true for any V in V. And secondly, let me define one-dimensional subspaces V1 such that and V2 such that okay, then V is nothing but a direct sum of V1 and V2. And then the third one is that T is diagonalizing. Okay, now if you recall, if you have to express a vector space as a direct sum of two other vector spaces, then you need to show two things, that any vector in V can be written as an algebraic sum of vectors belonging in V1 and V2 respectively, and the intersection of V1 and V2 has to be null. Okay, all right. This is the same argument that we use to propose the idea of eigenvalues and eigenvectors, and specifically eigenspaces, where we argued that each eigenspace is a one-dimensional subspace of the vector space, so that you actually, decompose the vector space into the number of eigenspaces, and this number is directly proportional to the size of your vector space. Okay, I mean, assuming that you have real and distinct eigenvalues throughout. All right, so nothing new. However, I mean, we have to see how we approach this problem. So let's just attack the first one, T square equal to I. And we know that T is a linear transformation going from V to V. So therefore, if I pick an arbitrary vector in V, then that will satisfy this, right? Okay, all right. Now this implies that this T square V, you know from eigenvalue eigenvector concept, that this is this, and so therefore you have lambda square minus 1 equal to 0. And clearly, I mean, for this is for non-trivial eigenvectors, right? And so this implies that your lambda 1 is plus 1 and lambda 2 is equal to minus 1. So you have two eigenvalues, and for each of the eigenvalues you have a corresponding eigenvector, right? So the corresponding eigenvector is V1 and this corresponding eigenvector is V2. I really don't need to know what those eigenvectors are, right? More importantly, I mean, if I come back to this, right? I mean, this is, I can rewrite this. I can rewrite this also in the following manner: is T plus I and T minus I times V equal to 0. Okay. Now, what is given to me is that T minus I is a non-singular map. So if T minus I is a non-singular map and V is a non-trivial eigenvector, I mean, that implies that T plus IV has to be 0, and that gives me TV equal to minus C. Okay, right? For any non-zero v in the vector space. Okay, all right. The second one is more interesting, right? You know that you have seen from here that your eigenvalues are real and distinct, right? You have seen here that your eigenvalues are real and distinct. Okay. Now, for each of those eigenvalues, you have defined two eigenvectors, right? V1 and V2. So you define, we define the following. We define one vector space V1, right? Which is nothing but this will span the eigenvector only, that eigenvector which corresponds to this, such that PV1 is equal to V1, right? Okay, this is corresponding to this eigenvalue plus 1, and we can also define another vector space, which is nothing but the span of the eigenvector V2. Now, since you contain these vector spaces contain just one eigenvector, this has to be a one-dimensional vector space, right? Okay, so V2 in V2 such that EV2 will be equal to minus. Okay, all right. Now, since the eigenvalues are real and distinct, the corresponding eigenvectors have to be orthogonal and therefore linearly independent. So therefore, what you have is that when you look at V1, V2, they are nothing, they have to form a basis for the vector space V, right? Okay. Now, what happens is, since you can clearly see there is no intersection between these two vector spaces, right? Because these vector spaces contain the vectors satisfying this equation, and this vector space contain the vectors satisfying this equation, so the intersection is 0. And also, I mean, I take any vector in V, since V1 and V2 forms the basis, they also span that vector space, correct? So any vector in V can be written as a linear combination or as a unique sum or a combination of V1 and V2, right? Right. So any vector in V can be written as V1 plus V2, right? I mean, you can choose your weights accordingly, but at any rate, you can express any vector in the vector space as a sum of V1 and V2, algebraic sum, right? For V1, small v1 in vector space capital V1, small v2 in vector space capital V2. And so therefore, since the intersection is null and the algebraic sum holds, I should be able to write the vector space V as a direct sum of vector spaces V1 and V2. This is trivial. We have seen this many times over because the transformation has real and distinct eigenvalues, right? Therefore, there is a diagonalizable matrix which we can cook up, and that diagonalizable matrix is written as a change of basis matrix, where you should be able to write P as P inverse, where P contains the columns of the eigenvectors, which is V1 and V2. Right? And the diagonal matrix is nothing but the eigenvalues of T, which are plus 1 and minus 1. Okay, so that's straightforward. Okay, all right, and I will probably stop here. This is just left as an exercise, not as a homework, right? And just leave this as an exercise. Most of these problems are actually cooked up by me, so sometimes, I'll just make small mistakes, so you can correct me. So I have a 2 by 2 matrix, okay? So I have a 2 by 2, T is a 2 by 2 matrix, okay? And its eigenvalues are lambda 1 and lambda 2. Okay. All right. Now I assume that lambda 1 is non-zero and lambda 2 is also non-zero. Okay. All right. Then T inverse is nothing but lambda 1, lambda 2 reciprocal, lambda 1 plus lambda 2 I minus, okay, lambda 1 plus lambda 2 I minus, okay, all right. I mean, this should not be hard. If you recall that eigenvalues are actually roots of a characteristic polynomial, and you start with a characteristic polynomial and factor out the characteristic polynomial in terms of its eigenvalues, your lambda 1s and lambda 2s are those factors, and take it from there. Okay, all right. It should be a simple enough problem. Okay. All right. So I guess you have a test tomorrow and maybe even today, and then you have a break, right? So when we come back, I hope you are refreshed, and we should be able to, move forward with inner product spaces and inequalities, more inequalities on inner product spaces, and more importantly, two very fundamental methods that we use a lot in data science. One is least square approximation, and the other one is orthogonal basis, creating an orthogonal basis from a non-orthogonal one. Okay, all right. So I'll see you whenever I see you. Okay. If the clarification that I gave regarding your grades is not satisfactory, you can email me and I'll be happy to answer your question. Okay. And I have also heard that some of you have complained that the second test was really easy. Well, these are quizzes, right? And I'm just testing your concepts on these quizzes. Okay. And I can make it as hard as you want. And I mean, let me know about the thoughts on the final test. And if you really want me to make it a hard one, I can. Don't worry about it. Okay. All right. Thank you. I'll see you next week.
Hello, sir.
Yep.
Sir, can you repeat that exercise that you gave? I just lost my connection for that moment.
The exercise that I gave. Okay,
Yes,
okay.
sir, yes.
Yeah. Just a minute. Okay. All right. Where is that? Damn it. Yes, okay. So the exercise is T is a 2 by 2 matrix with eigenvalues lambda 1 and lambda 2. And lambda 1 and lambda 2 are both non-zero. Then the inverse of T inverse can you see my whiteboard?
Yes, yes, visible.
Okay. So then the T inverse is nothing but this expression. So you see this expression, right? So lambda 1, lambda 2 raised to the power minus 1, which is nothing but a reciprocal of the product of lambda 1 and lambda 2 times lambda 1 plus lambda 2 times I, or I is the identity matrix minus T within the parenthesis. Okay.
Okay, sir. So when do we have to submit this?
This is exercise,
Or
not
just for?
homework.
Oh, okay.
Yeah. Yeah.
Okay, sir.
Yeah.
Thank
Okay.
you, sir.
All right. Yep.